Yes.
Limiting reactance is another thing that you should have studied in Chem 120. And the idea is that for the reactions we've looked at so far, everything has involved using excess amounts of one chemical or another. Always, I've been using excess, so I've assumed that there's more than enough of one reagent out there. But in reality, that's not usually the case. In reality, we have to measure out the amounts of all reagents that we deal with here. The only times that we really don't have to worry about this is when we have scenarios like oxygen being one of the reactants, because oxygen is abundant, it's not going to run out. If you're burning a candle, you don't have to quantify the amount of oxygen. It's essentially limitless. And so there's many different ways that you could come up with talking about limiting reactants. I know in Chem 120, the way I do it is by talking about ice cream sundaes. I say that you need this many scoops of ice cream for a sundae and this much chocolate and this many cherries. And it doesn't matter if you have 13 cherries. If you only have enough ice cream scoops to build 4 sundaes, that's what you're going to get, if that makes sense, right? You ultimately run out of one of the substances that you need. Okay, I just muted everyone because there was feedback somewhere. And again, please do unmute yourself to contribute. And then if you think you might be the one causing the feedback, just mute yourself again once you've talked. Okay, so, and your book talks about sandwiches, 2 slices of bread, so much meat, so much cheese, and some things will be left over. So let's look at this reaction here. It's one I've been using a lot the last couple days, the reaction between nitrogen and hydrogen to make ammonia gas. Everything here is a gas. And so what we would expect here is that if everything is mixed in the correct ratios, specifically the reactants. So for example, for every 1 mole of nitrogen, you mix in 3 moles of hydrogen. That's what we would call a stoichiometric mixture. Theoretically, if you mixed 1 mole of nitrogen and 3 moles of hydrogen, you would get 2 moles of ammonia. And if you mixed 1/10 of a mole of nitrogen with 0.3 moles of hydrogen, you should get 0.2 moles of ammonia. I just divided everything there by 10. Now, when we get to talking about equilibrium in chapter 13, we see that for this reaction in particular, the situation is a lot more complicated than that. But for right now, let's just assume that every reaction that we have follows whatever we have written right here, and it goes to completion. So if we look, for example, at a stoichiometric mixture, looking at a figure I took from the textbook here, every 1 mole of nitrogen is reacting with 3 moles of hydrogen. You see how everything is kind of nicely grouped here? So 1 mole of nitrogen, or 1 nitrogen molecule, 3 hydrogen molecules. 1 nitrogen, 3 hydrogens. If everything can be grouped exactly in a perfect ratio like that, that's called a stoichiometric mixture. And at the end, if we had all these little imaginary bubbles, every one of these would change into 2 ammonias. And what we would find is all the nitrogen and all the hydrogen has been completely consumed, and we have only ammonia, and everyone lived happily ever after. Okay? Again, not reality, but this is how things should go. This is a non-stoichiometric mixture. What do we have? What are we going to, what do we have more than enough of? What do we have excess of, according to this picture?
We have more nitrogen than hydrogen?
Yeah, and I don't want to say more nitrogen than hydrogen. We have, according to the reaction ratios, we have more nitrogen than hydrogen. Because if we look here, there isn't enough hydrogen to go around for all of the nitrogens on the starting point here. And so therefore, what was in excess? The nitrogen. And what did we run out of? We ran out of the hydrogen. So we say hydrogen is limiting. A vitally important thing to grasp. if this reaction goes to completion, as we're going to expect, the limiting reactant is completely used up. Its concentration is 0 at the end of the reaction. We have none of it. And that's what we see with hydrogen. We have no hydrogen left at this point. So we're going to look right now at a couple different ways of addressing limiting reactant problems. Method number 1 is probably the way that you're used to seeing it. And that is what we do is we solve the stoichiometry problems twice, once for each of the reactant, and then we choose the smallest result. For example, in looking at this picture, how many ammonia did we make? How many ammonia molecules? We made 2, 4, 6. There was enough hydrogen to make 6 ammonia molecules. However, there was enough nitrogen to make how many ammonia molecules?
8.
Not quite.
How many hydrogen? 6.
How many nitrogen? How many ammonia?
No.
6.
2.
10. Okay. Look, for every 1 ammonia, and for every 1 nitrogen, you can get 2 ammonia, right? You had 5.
Wrong. Sorry.
Yeah, sorry. You had 5 nitrogen. So you have enough to end with 10 ammonia. In reality, you only ended with 6. Okay. So you had leftover nitrogen here. So there will always be some of the leftover still there. So ultimately, which is the correct answer in this situation? You get 10 ammonia or you get 6 ammonia, according to this situation. According to this situation, you can only get 6 ammonia because there's not enough hydrogen to go around. So there was enough hydrogen for 6 ammonia, enough nitrogen for 10 ammonia. The right answer is always the smallest. Okay? Because
So the limiting reactant would be the hydrogen because there's not enough to create more.
Exactly. So if we look at this, there's 9 moles. Let's say that each one of these molecules stands for a mole. Okay? There's 9 moles of hydrogen. 9 moles of hydrogen would be enough to form 6 moles of ammonia. There's 5 moles in this picture of nitrogen. That's enough to form 10 moles of ammonia. So which is the correct answer then, 6 or 10? It has to always be the smallest answer. Okay, so method 1. Staying with this problem real quick. We have 100 grams of nitrogen reacting with 3 grams of hydrogen to form ammonia. We want to know which is limiting, and we want to see how we know. We can't, by the way, just look at and say, oh, there's 100 grams of nitrogen and 3 grams of hydrogen. There's clearly way more nitrogen, and so that's limiting. I mean, excess. You can't compare the masses. Remember, you need to compare the moles, right? Always compare the moles. So let's go to our notes view here. And so I'm going to want to do the work up here. Good. Okay, so what we have to do is we have to look at the problem twice. Once from the perspective of nitrogen, and once from the perspective of hydrogen. Okay, so I have 100 grams of nitrogen. I need to figure out how much ammonia that's going to form. I can either figure out how many grams it's going to form or moles, either way. Do you agree more moles is more grams if we're talking about the same compound? More moles of compound X will always be more grams of compound X. So long as you're not changing compounds there, that's the case. Let's just go all the way to grams because I think that's going to be the easiest way to do this. Okay, so I want to get to grams of ammonia, so I do my usual dance of going from grams to moles. So if we look on the periodic table, you'll see that there are 28.02 grams of nitrogen. That's 2 times 14.01 is 1 mole of N2. We're going to ammonia, so every 1 mole of N2 will make 2 moles of ammonia. And every 1 mole of ammonia is 17 something grams. Did anyone calculate that already? 17 point? Anyone? No? All right, then I'll do it. 14.01 for the nitrogen plus 3 times 1.008 for the hydrogens is 17.03.
I had a question.
Yes.
Going to grams of ammonia here is optional, right? You could just stop at moles.
Yeah, that's what I was just saying a second ago is you could stop at moles because the smaller number of moles would always be the smaller number of grams. Correct? So 1 mole of ammonia is always going to have less mass than 2 moles of ammonia. So you could. I just figure, you know what, I've already started writing it out. It's only like 5 more button pushes. So to me, it's more effort to stop and then go back. But your choice. Okay, and then down here, oh, I didn't find an answer. I'll go back and find an answer in a second. And so then we have 3 grams of hydrogen. And hydrogen would be 2.016 grams of hydrogen is every mole. And what number goes in front of the moles of hydrogen?
3.
3. Very good. So from the balanced equation, every 3 moles of hydrogen gives you 2 moles of ammonia. And every 1 mole of ammonia still has a mass of 17.03 grams. So I have 100 divided by 28.02. Times 2 times 17.03 is giving me in the in the first problem, 122 grams of ammonia. Why is that immediately obvious? It should be that that's the wrong answer. Something about this problem, reread the problem, and it should be immediately obvious this is the wrong answer.
We have more grams than what we started with.
Exactly. You started with 100 grams of nitrogen and 3 grams of hydrogen, and the only chemical you formed is ammonia. That's important. There is no other chemical other than ammonia. You have just either won the Nobel Prize or you're going into an insane asylum, one or the other, okay? You have created mass out of nothing. Congratulations. Yeah, 100 grams plus 3 grams cannot be more than 103 grams. So I already know this is not the right answer. Does that make sense to everybody? Right? You can't possibly get more than that. And when we have these problems specifically, these are the easiest ones to deal with, combinations for these kinds of problems, okay? So I can already see that the next answer is the right answer. So I've got 3 divided by 2.016 times 2 divided by 3 times 17.03. And I am getting 16.9. Is that what you guys got? Yeah.
Yeah.
Okay.
Yes.
Great.
Yes.
Okay. So which of these, which reactant is limiting? Nitrogen or hydrogen?
Hydrogen.
Hydrogen.
Hydrogen. And you know because it produces the,
Least amount.
yeah, the lesser amount of ammonia or product.
Also, it's more realistic, right? Because it falls in the bounds of the amount of samples we have.
Yes, I would agree. By common sense, it looks like it's going to be the right answer. But even with common sense, I would still check. Definitely check, just in case.
Okay.
Yeah. Because remember, the mass of nitrogen is 14.01 grams per mole. Hydrogen is 1.008. If I change that number from 3 to about, what, 12, 13, then the hydrogen would be in excess. I don't need to get it that much higher because, again, hydrogen is so light. It's such a low mass compared to ammonia. I mean, compared to nitrogen. Okay, so how many grams of ammonia were formed in reality? 16.9 grams. Okay. I need to make a very important point right now. The use of this value is totally useless. It has, do not use it in any way whatsoever. Don't try to use it in another part of the question. It is a totally pointless, it's a totally hypothetical. Unless we change unless we change the circumstances of the problem, then you might find a way to use it. So you could use this to go back and say, well, if I did want to make this so much ammonia, how much hydrogen do I need? But I also could have used this number. So this is a fantasy land value. I see people using these all the time in problems, and it's like, no, it's not an answer of any use under these circumstances, okay? So please don't say, oh, the real answer, you know, no, it's useless. Just throw it away. It's just about as useful as getting negative masses, okay? What else remains in the flask and what is its mass? Okay. Now, there's 2 ways of answering this. Method 1. Since there are only 3 chemicals in the reaction, or 3 substances in the reaction, and I'm going to be very clear about this, in this reaction. And what do we know? We know the masses of how many of them. We know the mass of the, at the end. At the end, we know the amount of the ammonia, correct? And we know the total mass. So we know the amount of the product. So this is the condition. It has to have only three. It has to only have three chemicals in the reaction. We can use law of conservation of mass. Or mass conservation for short. So in other words, we started with how many grams of chemicals? We started with 100 grams plus 3 grams. What's the sig digs on that? Yeah, 100 grams plus 3 grams. It's 103 grams, right? We got 16.9 grams of ammonia. And what do we know about hydrogen at this point? Very important. What do we know about hydrogen since it was limiting?
It was all used up, right?
It was all used up. So we got 16.9 grams of ammonia, and we have 0 grams of hydrogen left because it was limiting. How do I find the amount of nitrogen left over? I started with 103 grams. I have to end with 103 grams.
You subtract 103 by 16.9.
Exactly. So this means, so 103 minus 16.9, which is that, what is it, 86? Mm.
86.1.
Yeah, okay. So after sig digs, because we can only go to the ones place, there's 86 grams of N2 left. That method is by far the fastest if there's only 3 chemicals in a reaction, because you don't have to write all those words out. I only wrote all those words out so that you can recognize the situation and can do it again if you recognize that. Okay. The next method always works. And that is you just find the amount of excess reagent used up. By the way, we use excess to represent the word excess. And then we subtract it from the starting amount. Okay. So how do I find how much nitrogen was used up? Again, don't go to 122. Bad number. Ignore it. I can start with either 3 grams or I can start with 16.9. That's your choice. Either pick 3 grams or 16.9 grams. Or if you're kind of clever, it's 16.9 minus 3, but I'm not going to tell you why at this point. But well, let's just say we need 3 grams of hydrogen. We're running out of space, so I got to keep this kind of small here. There are 2.016 grams of hydrogen. Reacts with is 1 mole of hydrogen. Every 3 moles of hydrogen uses up how much nitrogen?
Just one.
Just one, yeah. And a mole of N2 is 28.02 grams. And my guess is that this is going to be 14 point something. Did anyone solve that yet? No. Okay. So 3 divided by 2.016 divided by 3 times
I got 14.
Exactly.
13.89, rounded 14.
Okay. So yeah, 13.9, because I got to be careful about my sig digs for a second there. So 13.9. And so therefore, 100 grams of nitrogen is what you started with, minus 13.9 grams left. I mean, used up, means that we have 86 grams remain. Okay, again, this was the amount you started with. $13.9 is the amount you used up. And so 86 grams of nitrogen are left over. Okay. Any questions about that?
Like you said, you can just subtract 16.9 grams of ammonia from 3.00 grams of hydrogen, right?
Yes.
You subtract 100 from that.
Yes, and that works on this problem because it's a special case. There's only two chemicals. There's only two elements, nitrogen and hydrogen. If this had nitrogen, oxygen, and hydrogen, this wouldn't work, right? Because this would be only one element or something. So that definitely works in this problem. And I would encourage you to use it. If you know it works, definitely use it. Just always be careful, that if you're dealing with two chemicals and you're subtracting one, you can definitely do that. But if this was NOClH2 and this was H2, you couldn't get away with that. So you have to be very, very careful. But yeah, that definitely works. Okay. Method 2. So I know that sounds like two methods right there. Method 2 is initially going to seem very unattractive. I promise you it is, especially when we get to Chem 140, much more useful because you're going to, in Chem 140, often need to know the amount left over. Knowing the amount of a chemical left over is critical in many situations. It doesn't tend to come up as much this semester. Not only that, it will be very useful because what we're going to use right now, called Bca tables, become modified into what are called ice tables in Chem 140. There's two different types. So this is kind of the getting used to it at first. So BCA stands for before, change, after. And so the way this looks is we write the balanced chemical equation at the top. We have the first row labeled B for before. And then we put the amount of each chemical that's there in moles. Or, as you will see later, or millimoles. Have any of you talked about millimoles yet? I don't think they brought it up. No. What is a millimole? Just from the word. What should a millimole be?
1,000 of a mole.
What's that?
1,000 of a mole, right?
1,000th of a mole. Exactly. Exactly. And the reason those become more important later is because what volume unit do we almost always use in this class?
Milliliter.
Milliliters, yeah. And so later on when you work with molarity, it's much easier to deal with millimoles than it is to deal with moles. If you remember doing calculations last semester with molarity, you ended up getting a lot of moles that were this times 10 to the minus 3 or 10 to the minus 4. And it gets to be a pain keeping track of those zeros or keeping track of scientific notation. And millimoles are an easier way to go. For right now, we're going to just say moles. And this whole discussion hopefully will reinforce in your head that not grams, moles are what we need in the table. So everything in the table has to be moles or some derivative of moles. Okay. Under each product, since we haven't started the reaction, we put 0. All right, so let's look at this last problem in the form of a Bca table. So before, I convert everything that I have to moles. And you need to know how to do that fast. How do you quickly change something from grams to moles? Without writing it all out, you just take its mass and divide by its molar mass. Okay? So without writing out all the steps, mass over molar mass is always moles. It's worth knowing that. So mass over molar mass is moles. So where did I get the value for nitrogen? It's 100 divided by 28.02. That's the 3.57 right there. And if we want to write a note on that, we certainly can. Okay. So that's 100 grams divided by 28.02 grams per mole. That number is 3 grams divided by 2.016 grams per mole. Okay. Why is there a 0 under ammonia? Because according to the reaction, what did I mix together? I mixed 100 grams with 3 grams. I never add any ammonia to this, right? Ammonia is what's formed later. So you are starting with no ammonia. Can we all accept that? Yeah, it gets formed later. Yeah. So the B is, what we're doing with the B table is we're assuming no reaction has occurred yet. Okay, we don't know what's in excess. But can we agree on one thing? And this is the important thing to understand. The after table, what is the lowest possible number that you can have in an after table? At the end of the reaction, what is the smallest possible amount you can have of any chemical?
0.
0. Can you ever get a negative mass or mole?
No.
No. Okay. So the key for understanding the next part is if you get a negative answer, you did it wrong, which is fine. Knowing you did something wrong will immediately tell you what the right answer, as you're going to see in this next part. Okay. This is the tricky part right here. I want to figure out if 3.57 is the limiting reactant. If it's 3.57 is the limiting reactant, how much will be left at the end, always, if this is limiting?
0.
0, good. So that means the change row would have to be minus 3.57. Does that make sense? If this is the limiting reactant, you lose all of it, always. If this is the limiting reactant, you lose all of it. So let's just assume, because you've got a 50-50 guess on which one is the limiting reactant. Let's assume that the nitrogen is the limiting reactant. What we do is we go ahead and we say, okay, 3.57 times 1 over 3 times 3 over 1. Where is this coming from? This is the tricky thing. The 3 over 1 is
The ratio?
the ratio, yes. Every 1 mole of, oh, I don't have it up here. Where is it? It's over here, but upside down. Good. What you do is you just go ahead and say, for every 1 mole of this, I get 3 moles of this. So it's always what you're looking at over what you're starting with. What you're interested in over what you're starting with. If nitrogen is the starting one, it's 3 over 1. So I'm going to take minus 3.57. Don't fill this in. Don't fill this in. And this would be minus 3 over 1 times 3.57. Why is that obviously not going to work?
Because you get the negative.
Yeah, negative 3 times negative, that's going to be like more than negative 10, isn't it? And when I add these together, 1.49 and negative 10, this would give me negative hydrogen. Okay, so that doesn't work. Nitrogen is not the limiting reactant because it would give me a negative amount of hydrogen at the end. Can't do that. Does that logic make sense to everybody? You can never end up with a negative amount. So this can't be the limiting reactant. Okay. And I just simplified that right here by saying 3.57 times 3 is 10.7. Since that's more than I started with, nitrogen can't be the limiting reactant. Okay? I should have put another sentence in there. Let me put another sentence in. Okay. So N2 can't be limiting. And so since only one of them can be limiting, if it's not N2, it must be H2. Now you fill in the change row. And so let's look at how we do this. So anyway, going back to that. The change row. We've already decided that the hydrogen is the limiting reactant, and we've already decided that the limiting reactant must get used up. That's the definition. So minus 1.49 moles. We've used all the moles here. So the amount at the end is going to be 0 here. How much do we lose on this side? Do we lose 1.49? No, because it's 3 to 1. You need to take 1.49 and multiply it by what number to figure out how much nitrogen you need. This is what you're starting with. This is what you're looking at. So you multiply by what fraction?
1 over 3.
1 over 3. Good. 1 over 3. And that's negative 4.497. How much ammonia will you make? 1.49 times what fraction? You're starting with hydrogen, you're making ammonia, so
2 over 3.
2 over 3. Yeah, 2 over 3. And ammonia is a product, so it's going to be positive or negative change.
Positive.
Must be positive, yeah. So reactants are always negative, products are always going to be positive. Oops, sorry. Eek, there we are. So this is just accounting, essentially. So how much hydrogen is left? That's easy. We just add these rows together. At the end, there's 0 hydrogen. How much ammonia is there in moles? 0 plus 0.993 would be 0.993. And then we just take this number here to find the number of moles. Okay. So again, there should always be a 0 under the limiting reactant. And if you got a negative number, you picked the wrong limiting reactant. Good. So at the end of the reaction, you have 3.07 moles of nitrogen mixed up with 0.993 moles of ammonia. If you want to get these to grams, you do exactly the opposite. Instead of dividing by the molar mass, you multiply by the molar mass. Yeah. And the number of moles is always going to be bigger. I'm sorry, the number of grams will always be bigger than the number of moles, right? Even for hydrogen. So you'll know because the number's going the right way. So this says at the end I have 86 grams and 16.9 grams. This was probably not the easiest way to do it for this problem. But it becomes very easy as the problems become more and more complicated. Okay, any questions on how did I do this or why did I do that? You know, anything like that? No. Oh, and one change I would make is I would always write the word mole on my table so I know what unit I'm talking about, whether it's moles or millimoles. Never do it with grams. Okay, so let's do a BCA table for this problem right here. So this is page number 312. Okay, so I'm going to leave myself some space to do some work. Before I can do anything, I'll probably need to know the atomic masses and the molar masses of everything, right? I need the atomic masses and the molar masses of everything. So let me write those out real quick. So carbon is easy. Carbon is 12.01 grams per mole. These are grams per mole. Iron is easy. Just look it up on the periodic table. 55.85. Carbon dioxide or carbon monoxide is relatively easy. That's 12.01 plus 16 would be 28.01. And really, to begin the problem, I don't even need the two products. I really only need the two reactants. Fe2O3 would be 48 plus 55.85 times 2, 159.70. Okay, so what goes along the top of a BCA table? The
balanced equation.
Good, good. And I'm going to write here moles, so I know that that's my unit. Okay, so Fe2CO, I'm sorry, O3, plus 3C gives me 2 irons, plus 3 carbon monoxide. So I'm trying to figure out the mass of each product formed and the mass of any leftovers. Good. So the first part is the before. So all I do is I take the masses and divide by the molar masses. So 180 divided by 159.7 is 1.13. Carbon is 45 divided by 12.01, 3.75. Notice the 3 doesn't enter at all into this yet. I'm just finding the moles from these numbers right here. How much iron is there and how much carbon monoxide is there in the beginning?
0.
0, because they are products, right? Good. Change. Let's assume that, and we're going to do this with a pencil. Let's assume that the iron 3 oxide is the limiting reactant. If it's the limiting reactant, then what would have to go here? If it's limiting, this would be, we lose all of it, minus
1.13.
1.13. Good. And then over here, we would lose how much? We would lose 3/1 times 1.13. Why 3/1?
Because of the ratio.
Yeah, for every 3 that you produce or 3 that you need, you start with 1. So remember, you always, if you're starting with this number, that's the denominator. The other numbers are the numerators. So minus 3/1. Is that going to give me a positive number or a negative number if I do this addition right here?
Positive.
Positive, so that means we're okay. Okay? If you got a negative number, that means you picked the wrong limiting reactant. And life is not over. You just erase, and you pick the other one. Okay. Good. Iron. How much iron do you get? Plus what fraction?
Is it 3/2?
2/1. Because remember, we're looking at
Oh.
the limiting reactant was the iron. So plus 2/1 times what number? Everything is relative to iron 3 oxide. Plus 2 times 1.13. And this would be what over here? Plus what? What fraction?
Repeat.
3/1.
3/1 times
1.13.
1.13.
Yeah. Good. So everything here is some fraction times 1.13. I know I didn't write it that way up here, but these were all something times 1.49, right? All of those numbers were something times 1.49. Okay. How much do we end up with of the limiting reactant? Always 0. Good. The next one, 3.75 minus 3 times 1.13 would be 0.36. This would be 2.26. This would be 3.39. This is really what we would call just a spreadsheet, okay? You can use a computer to do this if this were the real world and it were a more complicated reaction than this. The one thing that worries me again is that you remember reactants are always negative changes, products are always positive changes. You always lose reactants and gain products. The fractions are always once you've determined the limiting reactant, it's always the numerator is the other chemical. So 3. The limiting reactance coefficient is the denominator. So 3/1, 2/1, 3/1. Good. And the final question was, what was the mass of each of these? So how much is left over of everything at the end? This one's easy.
0.
Good. This one would be that times what? 12.01, right? These are all moles, so grams per moles. This one would be times 55.85 grams per moles. And this would be times 28.01 grams per mole. All right, so not too hard to do that. So 2.26 times 55.85 is 126 grams per mole. Or grams, excuse me. 3.39 times 28.01. And please do check my numbers if these are off. 94 points, this is 95.0. And 0.36 times 12.01 is 4.32 or 4.3. Okay, so that's everything that's left over at the end, assuming we have a reaction that goes perfectly to completion. Any question about where did I get this? Why did I do that? Any kind of those questions about this? How could I use the law of conservation of mass to confirm that my answers are probably correct?
Check to see if they add up to 180, or to see if you have to match them up, add them up, and see if they if they equal their original masses.
Exactly, exactly. So the original mass was 180 plus 45, which is
225.
225 grams. So all of this should add up to very, very close to 225 grams. Again, because of significant digits and rounding errors, it might be a little bit off. So 4.3 plus 126 plus 95 gives me 225.3. Again, that's probably a significant digit issue over here. But that's another nice thing about it, is it makes it very easy to see that you probably have gotten the right answer. The only way you could have a wrong answer right here would be to be wrong twice. And this is another example in chemistry of two wrongs make a right, okay? If you're wrong here and wrong here by just exactly the same wrong numbers, they would cancel out. But other than that, and it's highly unlikely. So it's another nice tactic for this. The other nice thing about this is in the real world, what if you're running this reaction over and over and over, day after day after day? You don't want to be doing this by hand every single time. You put this in a computer, you just type in the new numbers, boom, you have the answers. Easy. And so it's a nice technique to use. As I said, the most important reason is because I'm going to want you to use it in Chem 140 when we get to equilibrium. We use this same thing with equilibrium. The problem with equilibrium is instead of numbers, there starts being x's. And you start having to solve equations with x's in there instead. Because reactions don't go all the way. They only go part way. And if you're really solid at doing this, then doing equilibrium will be a breeze. Okay. The last thing is not too difficult here, and that is theoretical yield, actual yield, and percent yield. Okay. In this class, we make a lot of assumptions. One of the first assumptions that we're going to make is, as we've seen all throughout here, is we've assumed that every reaction goes to completion. They all the way finish. Okay. And that's not true. What did we assume about gases in 120? What was the big assumption about gases? We said that they followed what law? PV equals nRT.
Ideal gas law.
Good, good. The ideal gas law, which in turn assumes we followed something called Boyle's law. We kind of deceive ourselves because no gas really perfectly follows it. But the thing is, as we'll see in chapter 5, the ideal gas law makes life so much easier than trying to figure out things to more precision. And if we are okay, except if we are fine with an answer which is very close to the right answer, we're okay. Most of the reactions that we do in this class go almost all the way to completion. And so we're making this assumption that this is what you get in these problems. We assumed that you used up all of the starting chemical, the limiting reactant, and everything goes here. What are some problems, though, in reality? Think about this as a chemist. If you're trying to collect the iron at the end, physically, how are you going to probably collect the iron? Just think about what you've done in the lab before, or what you've seen other people do in the lab. How would you get, what kind of a container is this probably in? It's probably in a metal container, right? Or a glass container. How do you get it out? You have to go in and scoop it out. Are you going to get every single little bit of it? No. So even if the reactions seem to go to completion, there's always going to be some that you leave behind. The other problem is that almost all reactions have some competing side reaction, which means that if you're taking this reaction here, yes, it makes iron and carbon monoxide, but it's probably going to make some carbon dioxide too. And if it makes some carbon dioxide too, that throws off this number, doesn't it? And some of that iron, instead of making being this, it might make iron 2 oxide. So there's always side reactions. So in the real world, you don't get 100%. Always something happens to divert it off. And so that's why we have percent yield. Percent yield is a measurement of two things, really. How good a job did you do as a chemist, first of all, in collecting all your products? And also, how good a reaction is this really? When I, as a chemist, go and I look up some reactions, it will tell me that the percent yield for this reaction is expected to be 45%. That means that these chemists are experts. They've tried it over and over and over. And with everything they've done, they never get better than 45% of what they expect. That's disappointing because what does that mean? If you only get 45% of what you expect,
you're losing a lot of your substance to other things.
Yeah, to other things or just flat out waste, right? And can you throw chemical waste in the trash can?
No.
No. If you're a chemical industry, that's tons of waste. And you have to pay for some way of getting rid of it or changing it to something else. So what is a great reaction? A great reaction is one that gives a percent yield of very, very close to 100%. The further you get away from that, that's not a good reaction, or you're not a good chemist. Okay, one or the other. So hopefully it's a good reaction, and we can get through this pretty well. Okay, so as I've said here, many reactions, if you look them up in the research, have less than 100%, and that's not your fault. They've done it, and they've proven that you can't seem to get better than that using a certain method. Okay, so an actual yield. Theoretical yield is the amount you should get according to what? This is important to understand. If I say a theoretical yield, that's these answers. Those are the paper answers. The answers that I got here on these problems, these are all theoretical yields. I popped the number in that I was given. This is what I should get because it's according to chemistry theory. Does that make sense for theoretical? You don't even have to do the experiment to do the theoretical yield other than measure the amount you're starting with. Once you've measured the amount you're starting with, you know the theoretical yield. The actual yield is what you measure at the end. You have to actually do the experiment to get the actual yield. And what must always be true? Actual yield compared to theoretical yield. Can the actual yield ever be more than the theoretical yield?
No.
Why not? It should feel like a horrible thing in your soul if you get more the actual yield than the theoretical yield. What is wrong if you get a higher actual than theoretical? It implies you have broken
The law of conservation of mass.
Exactly. It says you broke the law of conservation of mass. You created matter where there wasn't any before, you know, so If you have a higher actual yield than theoretical yield, 99 times out of 100, that means that, and if you ran the reaction in water, what does that mean is probably still there? The reaction is still probably wet. Okay, you haven't gotten rid of all the water. That's almost always what it means. In reality, you never create a higher actual yield than a theoretical yield. It can't happen. It's impossible. If you can find a way to do that, you have created a new chemical law, and you literally will win a Nobel Prize and be a billionaire or a trillionaire. But so far, we have no way to know that that could ever happen. Natural law says it's impossible. Okay. So a chemist reacts 20 grams of hydrogen with excess nitrogen, and they get 84.5 grams of ammonia. I want to know what the percent yield for this is. So 20 grams of hydrogen is the starting amount. What do we call that number right there? The 84.5?
The reaction amount?
It's one of these terms right here. It's the theoretical yield or the actual yield.
Oh.
It says that they what? They actually got 84.5. Does that make sense? This is saying
So it'd be the actual yield?
Yeah, that's the actual yield. Because they're telling you their results. Does that make sense? Without doing any calculations, they said, this is what we actually got. What do I have to do to find the theoretical yield? I have to actually do the problem. Okay. The theoretical yield is, again, all the stuff we've been doing so far in the chapter. We have to convert the 20 grams of hydrogen to ammonia. So that's the question we answer here. How much ammonia should we have gotten if the world was perfect and everything we did was perfect? Okay. So am I starting with 20 grams or 84.5 grams? What am I starting with?
20 grams.
20, yeah. 84.5 doesn't enter in at all. That's just saying that's what they measured. The theoretical is based on these numbers. So 20 grams. Oops, that's an 8, not a G. Sorry. Put a G there. And then I've done this problem a million times already above, so I'm going to go really quickly through it. Every 2.016 grams of hydrogen is a mole of hydrogen. Every 3 moles of hydrogen makes, sorry, I'm going so fast my brain is out of sync with my hand. 3 moles of hydrogen makes 2 moles of ammonia. And a mole of ammonia was 17 point, was it 0.03? grams. Okay. Let me just double check that number.
Yeah, it's 17.03.
1703, yeah. 17 point something, but okay, so nothing I can cancel. So I've got 20 divided by 2.016 times 2 divided by 3 times 17.03 is 113. Okay. This, remember, is our perfect answer if everything went perfectly. So we call that the
Theoretical yield.
theoretical yield. Good. Percent yield, which is what we want, is 84.5 grams over 113 grams times 100%. And again, always be prepared to make sure that this must be less than 100%. If it's less than 100%, you've made an error. You would never want to turn in a lab report saying you have more than 100% yield without making it obvious that you know that that's wrong and trying to explain how that could have happened. Okay. And again, the answer is almost always you forgot to dry all the water off. Okay. 74.8%. Is this good? Is it bad? It really depends on the reaction.
Professor?
Yeah.
Should we round that 113 since it's like an intermediate computation? Should we be rounding that?
No, you would normally not want to round it, but we're going to end up with 3 significant digits at the end. So in other words, 112.6. Yeah, if I hadn't rounded it, I would have gotten what? 84.5 divided by 112.633. So what would that be? 75 point. Yeah, I mean, it's still within the realm of possibility. 74.8, 75.0. Those are still close enough that it would be considered, you know, within significant digits. What do we call the last significant digit again, anyway?
The uncertain digit.
The uncertain digit, good. So we might be off by that amount. Okay. Are any of you taking physics right now with Professor Vaca? Or have taken it?
I'm taking it
I
right
finished the physics series.
Yeah, he talks a lot about the uncertainty measurements, right? He does the error analysis.
Yes, we do that in lab all the time.
Yeah, which is very valuable and which also takes a huge amount of time. And which I say you will learn how to do in analytical chemistry if you take it. And if you already learned it in physics, the same thing applies. So you would find, in answer to that question, which was an excellent question about should I have rounded off, you'll find that, you know, these numbers always have a certain amount of wiggle room. They're always going to be a little bit off some way or another. So, but yeah, it would have been better not to round that. So 75.0 would have been a better answer. I fully accept that. Okay. Any questions otherwise on this here? And the final thing I want to talk about what that means, and I didn't do a problem on this, and maybe I'll write a problem about it for later, but I want to put this in words, what this means. Let's say you repeated this over and over and over and over and over. If you repeated this over multiple times and you got this result, let's say it's 75%, then when you're planning your reaction, are you going to plan to get, you're going to always plan to get 75%. So that means instead of, if I really needed 113 grams, if I really needed 113 grams, should I have used 20 grams once I know how this reaction is going to act?
No.
No, because no matter what I do, if I use 20 grams, I'm going to get about 85 grams over here, right? So how much should you use? 20 times what number? This is tricky. If I use 20 grams, I'm not going to get 113. I'm going to get 85. Do I need to use more or less hydrogen?
More.
I have to use more, right? Because if I use less, then this is going to be even less. And yet, when I ask this question to a lot of people, they say, well, I'm going to use 75% of that. Would that make any sense at all?
No.
No, if I use less, I'm going to get less. I would use 100% divided by 75%. Okay? And then multiply it by 20. Let's take a look why. So 100% divided by 75% is what, 133% or something like that?
Yes.
Yeah, so I would always use not less, but more. I would use 133% of this. So 20 times 133%, I should use about 27 grams, 26.7 grams. And think about why. If I use 26.7 grams, I'm going to get a number here that's too big. And when I multiply it by 75%, I get the amount I really wanted. I'm not going to, as I said, work through these problems right now, but you just always have to remember this is how it is. And it's just like if you're cooking for a party. And I'm sorry I'm talking a lot, I know today, lots and lots and lots. But these are real world problems. If you're hosting a party for 20 people, how many people are you going to cook for?
25.
Yeah. Think about your friends. Do you have really flaky friends who bring their, other friend who brings their other friend who does this, and all of a sudden you are expecting 20 and 30 people show up? If you have those kinds of friends, always prepare more, okay? Same thing with a reaction. You always need to prepare more than you really want at the end. Not too much more, because then you have waste. All right, so that was all of chapter 3, and again, as I said, I want you to start thinking this way as a chemist, so that you start thinking about the law of conservation of mass a lot. It tells you a lot about whether you're on the right track or the wrong track. It tells you about a lot of shortcuts. And also, you want to think this way so you're kind of thinking better about yields. Okay. All right, chapter 4. So we started at 2:30, correct?
Yes.
Yeah, okay. Chapter 4. Any questions in general? Questions about life while I'm getting this? No? No? Okay. Everyone's life is good.
What's the meaning of it?
42. 42 is the meaning of life. Very good. Okay. Chapter 4. And the notes have been up on the website. So if I go and look on the Chem Class website, we're in Chem 130. There it is. Chapter 4 notes. So make sure you have them. I'm going to download these. Sorry, I'm putting you all on mental pause right now. Should have had this before class. For some reason, I forgot that we'll get into chapter 4. Okay, open document, chapter 4. Good. So if you needed to go quickly get something to eat or drink, you just had time to do that. All right. Chapter 4. What do I want to cover real quick? Because we're kind of limited on time. Let's go into, I'll just go through the whole thing for the time being. All of chapter 4 is not going to be on the first exam, okay? Only part of it will be. Let's get rid of that thing. Hold on real quick. Good. Okay. The purpose of chapter 4 is to discuss reactions which take place in solution, which are most of the reactions that we cover in Chemistry 130 and Chemistry 140. So if you think back to Chemistry 120, you studied Lewis structures, right? And you saw that water was a bent molecule. You also studied a thing called hydrogen bonding, which we will talk about more when we get to chapter 10. But the important thing to understand about water is that the oxygen atom is going to have what we call a partially negative charge. It's very attracted to positively charged ions in solution, okay? So this picture kind of comes out of the book. I don't really like the symbols that they're using at this point because they haven't really covered them yet, other than to say that we say that oxygen is partially negative. I don't like that too. I wish it wasn't there, but the book puts it there. And then these hydrogens are partially positive, which simply means that in solution, the oxygens are going to be very attracted to positively charged ions or cations, and the hydrogens will be rather attracted to negative ions. So we'll investigate that subject a lot more in chapter 8. Okay. Substances where we have a positive and negative charge in them are called polar. Just like a magnet has poles. We know that the Earth is like a giant magnet. It has a north pole and a south pole. A magnet has a positive and a negative pole. So what we say is a molecule like water is polar. This is the negative side of the pole. This is the positive side of the pole in that particular case. Molecules which share electrons equally, we call that, what do we call that sharing of electrons? What property is that called? Starts with an E, if anyone remembers from 120. Starts with electro.
Is it
Electronegativity.
Electronegativity, excellent, good. So something which is very electronegative does not like to share electrons in bonds. It's always about bonds. So when two things are bonded, the more electronegative one will try to pull the electrons toward it. If we don't have that kind of a phenomenon, if the atoms are similar electronegativities, that means they share. And if they share very well, they don't have positive and negative regions. They are non-polar. There isn't a positive and a negative. And again, we're kind of going through a lot of chemistry really quickly, and we'll come back to this in more detail later in the class. But we know that polar compounds generally mix well with other polar compounds, and non-polar compounds generally mix well with other non-polar compounds. In truth, non-polar compounds love polar compounds, and polar compounds reject them and say, no, we're not hanging out with you, sorry, that's the end of it. So when you try to mix oil and water, in truth, it's surprising, oil actually is attracted to water, and the water says, no, get away from me. And the water stays with the water, and the oil has to hang out with the oil. So like dissolves like. That's what we're going to say. Things that are similar in structure stay with things that are similar in structure. Okay. So this is kind of showing the degree of attractions that we have between water molecules. You have the negative parts of a water molecule and the positive parts of a water molecule. So these are attracted to each other. And again, what term did we use for this attraction when you talked about it in Chem 120? It was called a what kind of a bond, even though it's not really a bond?
Hydrogen bond?
That's called a hydrogen bond. Excellent. And again, we'll talk more about that later, but that is an attraction between these water molecules, a hydrogen bond. Good. So when we go to dissolve something in water, we have a couple things to fight about. Well, not us, but the molecules. First of all, water molecules love one another, and they are attracted to each other. If you put something which is ionic in water, the ions like each other, and they're very attracted to each other. But when you mix these things together, what starts happening is new attractions are possible. The ions, the positively charged ions, will be very attracted to the negative parts of a water molecule. And similarly, the negative ions will be rather attracted to the positive parts of the ions that are in water as well. And so in many of these cases, what we see is that the compound will dissolve. It will abandon its old attractions in favor of new attractions. One of the big things in this semester's class is we look at why. Well, actually, we don't look at why. We look at the calculations which explain why it happens. We look more at why next semester. But we will see that there's an energy reason for why this happens. Okay, something you didn't talk about in 120. So, some terms though. Whatever you try to dissolve in water, or the solution, or the, excuse me, whatever you dissolve is called the solute. Whatever is dissolved in the solution is called the solvent, okay? The solution, sorry, the solvent is what takes in the solute. And then the two parts together are called the solution, okay? As I mentioned a second ago, when you put an ionic compound in water, an ionic compound is a crystal lattice. It is kind of, to an extent, ripped apart within the water, and the ions go off with the water molecules. When an ionic compound is put into water and it separates out into ions, we don't just say it dissolves, we say it dissociates as well. That means the ions separate. Okay. So this is an illustrated model trying to represent what dissociation looks like. This is a picture of an ionic compound off to the left. You see the cations and the anions. The water molecules surround it and then form what we would literally call a cage, a hydration cage. They surround the molecule. And if you look very, very carefully, like if you look at this part of the picture right here, sorry. Let's see if I can blow that up a bit. Now, there we are. Good. Which atoms, the red are the oxygens and the white are the hydrogens, which of the atoms are trying to be closest to the cation in the picture?
The oxygen.
The oxygens, the more electronegative. Good. And which atoms are more close in the picture to the anion?
The hydrogen.
The hydrogens. Good. Okay. So this is again called dissociation. Dissolving and dissociating. Dissolving is just a visual term. If you put something in water, you stir it, and the solution appears to be homogeneous, it's dissolved. It has to be ionic to also dissociate. A solution that has ions in it is able to conduct an electric current, and in those cases we call those electrolytic solutions. You should have talked about this also last semester. A solution which is able to dissociate a lot and make a lot of ions, any solution with a relatively large concentration of ions, is a strong electrolyte solution. Anything with essentially no ions is a non-electrolyte solution. I think those are easy to understand. Strong electrolyte, lots of ions in the solution. Non-electrolyte, essentially no ions. There is an in-between picture called weak electrolytes. And really understanding weak electrolytes requires a little bit more chemistry, and I don't want to really go into that just now, other than to say that they have a low concentration of ions, and in Chem 140 we investigate more why. This is the ultimate test that we kind of use here for electrolytes. If we put a solution which has two electrodes which are not connected, So there's air in between those electrodes. The air doesn't conduct the electricity. An electrolyte solution will act almost like a wire in a way. They will help to conduct the electrons across. The ions will act as little shuttles. They basically conduct the electrons from one side to the other. If there's a lot of ions, we get a bright light bulb, a strong electrolyte. Very few ions, we get a dull light bulb. And essentially no ions means that we get what we call a non-electrolyte, and the light bulb does not glow at all. Okay, so the most important thing that you understand right now about this is what gives you a strong electrolyte. Number one, any ionic compound which dissolves in water. Okay? Because if it's ionic and it dissolves, it also dissociates. That means there's lots of ions in the solution. It will conduct electricity. So that's number one, any ionic compound which dissolves in water. Number two, strong acids, which are acids which dissociate. They give you H+ ions, which we call protons, and an anion. And for right now, the three most important ones to understand of these are hydrochloric acid, nitric acid, and sulfuric acid. There's also hydrobromic, hydroiodic, and perchloric.